Hello everyone! Today we are going to break down a topic that is actually quite simple, but oh so powerful in vector algebra. We're talking about multiplying a vector by a scalar. So let's get right into it.
So think about this for a second. You're scrolling through YouTube Shorts or Instagram Reels, and you see a video that just explodes. One day it has a few hundred views, the next day it's literally everywhere. How on earth does that happen? Well, it gets a massive boost, right? The algorithm picks it up and scales it. Now, what if I told you that we can do the exact same thing to our vectors? We can give them a boost, to scale them up, or even scale them down. This one idea, this boost, is the secret to understanding scalar multiplication. Okay, so this idea of a social media boost is a nice way to think about it. But how does this translate into the proper language of mathematics? Let's have a look at the formal definition from your textbook. Right, here it is. Now, don't let the formal words intimidate you. A scalar is just a fancy name for a regular real number. You know, like 2 or -5, or even a fraction like 1/2. We often use the Greek letter lambda to represent it. And the definition says the new vector is collinear. This is another simple idea. It just means the new vector lies on the exact same line as the original one. And this picture shows you exactly what collinear means. If you multiply by a number bigger than 1, like 2, you're stretching the vector. If you multiply by a fraction, like half, you're shrinking it. And what if you use a negative number? Well, it just flips the vector around completely. So it's just stretching, shrinking, or flipping. It really is that straightforward.
So whenever we apply this boost, this multiplication, it has two main effects on our vector. First, it can change its power, or what we call its magnitude. And second, it can change its direction. Let's break down both of these effects.
First up, magnitude. The length of our new vector is simply the length of the old one multiplied by the absolute value of our scalar. Now, why the absolute value? Those two bars around lambda. Well, because length can never be negative, right? Just like a video can't have negative views. So we always take the positive value of the scalar when we talk about length.
Okay, and what about the direction? This table makes it super clear. If our scalar, lambda, is positive, the direction doesn't change at all. It's like a positive reaction to a video. It just gets bigger. But if lambda is negative, the direction flips by exactly 180 degrees. It becomes the complete opposite. And if lambda is 0, well, the vector just vanishes and becomes the 0 vector, basically just a point.
All right, so we've understood the concept. We've understood the effects. Now for the actual calculations. And I promise you, this is one of the easiest things you'll ever have to calculate with vectors. When your vector is given in its component form, you know, with I hat, j hat, and k hat, the maths is just beautiful. All you have to do is take that scalar, lambda, and distribute it. Just multiply it with the I hat component, then multiply it with the j hat component, and then multiply it with the k hat component. You're just boosting each part of the vector individually. That is literally it.
Okay, everyone, pay close attention now, because this is where we use our new knowledge to do something really powerful. This is a classic exam question. How to build a custom vector with the exact length and direction that we want. So here is our mission. We are given a direction, which is defined by this vector A, and our goal is to create a brand new vector. This new vector must point in the exact same direction as A, but, and this is the important part, it must have a very specific length, a magnitude of 7. So how do we construct it?
The first, most crucial step is to get the pure direction from our vector A. You see, right now, vector A has both direction and some length that we don't really care about. We need to strip away its current length so we are left with a pure direction blueprint. And in maths, this blueprint has a special name, a unit vector.
So what exactly is a unit vector? We write it as A cap, with that little hat on top. Its one and only superpower is that its magnitude is always exactly 1. It is the perfect directional guide. And the formula to find it is so logical. You just take the original vector and you divide it by its own length.
Okay, so let's calculate the magnitude for our vector A. First, let's identify the components. The number with I hat is 1, and the number with j hat is -2. Now we just plug these into our magnitude formula, which is just Pythagoras' theorem. So we get the square root of 1 squared plus -2 squared. That becomes the square root of 1 plus 4, which is simply root 5.
Perfect. We have the magnitude. Now we can finally create our direction blueprint. We just divide our original vector by this magnitude. So our unit vector, A cap, is I hat minus 2j hat, all divided by root 5. We now have the pure direction, isolated.
We are so close to the finish line. We have our pure direction, which we know has a length of 1. Now all we need to do is give it the power, the magnitude that the question asked for. And what was that? It was 7. It's time to apply the boost.
And here is the final step, the magic moment. We take our direction blueprint, the unit vector a cap, and we simply multiply it by the magnitude we want, which is 7. Because the unit vector has a length of 1, multiplying it by 7 gives us a new vector with a length of exactly 7. We distribute that 7 inside, and we get our final answer, 7 by root 5 I hat minus 14 by root 5 j hat. And we are done! We've built our custom vector.
Phew, that was quite a journey. But you've done an amazing job. Let's just take 30 seconds to quickly recap the key superpowers that you have learned today.
So remember, scalar multiplication is just giving a vector a boost to stretch, shrink, or flip it. The calculation is easy. You just multiply the scalar with each component. The magnitude gets scaled by the absolute value of the scalar, and if the scalar is negative, the direction flips. And please, never forget the master trick for exams. Your required vector is always the desired magnitude multiplied by the unit vector.
So there you have it. This wasn't just about a formula. It's about a tool that gives you precise control to manipulate vectors. You now have the superpower to stretch, shrink, flip, and even custom build any vector you want. That's a pretty powerful skill to have.